There you go.
Okay. So but they're not seeing this, are they? Oh.
There you go. This microphone here, we'll pick them up pretty well. You can walk pretty much wherever you want. You can hear.
It will follow. It's not following me now.
The tracking is not activated.
Oh, but this is going to be on.
No, what we'll have is we'll have just.
So I should speak here if I can.
Yeah. View full screen mode. There you go, sir. And you are ready to start whenever you like, and you have until noon.
Have until noon. Okay. We'll see. Oops. God, you have to be careful. The cannon. that's heavy duty. You know, you could probably kill roaches with this thing. So. Okay, so let's go ahead and get started.
Sorry. I was watching Reality TV.
Okay. Okay. And this morning's the big reality. The big reality is going to be Fortran. And so you guys had some C experience. I came in and asked you about where you were in terms of programming, and you understood some basic things which matched up well with what I'm going to teach. And so we're going to talk about Fortran, modern Fortran, and their various versions. So Fortran was at one time almost considered a dead language, and it was 1977. That's the old stuff, and nothing was done for years. And in 1970 or 1990, they revitalized it, and the standards committee has been progressing every 5 or so many years and updating it. So that's pretty good. And they have evolved the language quite a bit. So it's far from being a dead language. When C came along in the 90s, they thought, or 80s, they thought, well, Fortran was going to die, but it really didn't. It waned, and now we find that users are typically 50% of them use C, C++, and 50% use Fortran right now. And so we're going to talk about that, and in particular, how to write code in modern Fortran. That's what we're interested in here. Not so much the syntax, but sort of the concepts of using modern Fortran. Now, Lars Kosterka made all these slides, and I'm going to present those slides to you. So there might be a couple little details here or there I might not know. I can give you insights into some things that maybe weren't that clear, but I'll do the best I can with somebody else's material. So one of the first things we want to do is present the material in terms of you already knowing certain things. You already should, know one computer language. You understand the very basic concepts, and that is, what is a variable? When you assign something to something else, a value, on a line, that's assignment. You know what a compiler is for. That compiler makes machine instructions right away in a .out or a file that you execute. It doesn't have to interpret those on the fly like some other languages do, okay, like Perl and Ruby and things like that. So it's compiled to run fast, and that's the good thing. It's to run fast in high-performance computing. Okay, so Fortran's about doing, taking a formula, it's a formula translator, taking a formulation and making it run fast on a particular hardware. And you know what an executable is. That's the thing. On the command line, you just type that executable name and it runs. Okay, much like a script, much like you did with C the other day. And so what we assume that you maybe already know some Fortran, or you will at least know some by the time you get out of here at noon today. And you might be curious about what comes next, or the evolution of a language. We'll talk a little bit about that here. And then what are the choices? What are the choices for you programming? The worst thing you can do is start out and we're trying to do something. You have this formula, you have a scientific project, and you don't know anything about sort of the structure, the big concepts of the language, and you just say, okay, I got to do this. Here's the book. Here's how I do this, and just plug in these little things. Then you have a hodgepodge code of just things you wanted to do. And you should think more at a higher level in terms of management of things you want to do. And in particular, if you're writing code for somebody else to use, you want it to be understandable. You want it to be able to take it to different platforms. You want it to be somewhat portable. Okay, so we usually work with what the standards are. And what do we mean by that? Well, any vendor, Intel, PGI has the compiler, and they'll have extensions on that, special things for that compiler. Well, that's okay if you're always going to use that compiler on a particular machine, but usually you're going, if you have a good code, other people are going to use it on other machines. They'll want to compile it and use it over there, and then it may not work if it doesn't have the extension for that compiler, okay, on that particular machine. So you want to make things portable. And so that's what you want to do. And then you also want to stay away from, quote, the old Fortran 77, okay? We'll sort of show you some examples of that and some of the problems that it had. So it was the first attempt or first approach in standardizing something well across different platforms, and people used it for many, many years, and there's legacy codes out there with it, and so you might have to go read those someday, but hopefully nobody says, I want you to write this in Fortran 77. If you do, convince them that no, that's not the correct approach, or modernize the code and go from there. Okay, so a little bit more about motivation. We'll talk a little bit more about that, and then we'll talk about the modern Fortran. So one of the things is that Fortran 77, just like C, and even the language you learn, scripting language, they all have basic things in them that you use. And once you know one language, it's pretty easy to go over to another language and sort of figure out what's going on with the code, write parts of it. Maybe you may not be able to construct a big code right away, but at least you could do that. You could figure it out. There's lots of details that have to be worked out, but usually you can look at these things and tell what's going on in the code. And so we work with these things, variables. And these variables will be particular types. There'll be integers, real numbers, there'll be logicals, there'll be character strings, and that's pretty much it across the board. Then you have these things called vectors or arrays, where they're contiguous in memory and they're accessible with some sort of index. And I guess they're familiar with accessing things through indices, and that makes really fine. Makes things a lot easier to work with in terms of loops, because in a loop you have some sort of index and you access that variable according to that loop. That's good. Those are basics, all basic things. So we have our loops that are done repeated. We have the if and else's, because you have to make decisions on what kind of answers you're getting. So boom, you're off and running with these basic concepts here. We're not going to cover I/O, doing input output from Fortran. That could take a couple hours in itself, and so we're not going to cover that. And then, is that enough to write good code? And my statement to you is no. You need something more. And of course one of the basic things that Fortran 77 had in it is the subroutine, or the function call. Now in C, you have a function, and it's always returning a value. Sometimes you don't need that value. In Fortran, you can call a subroutine, and there's no value return that you put on an assignment statement. So you call a subroutine. You have a function usually that returns a value into something. Okay, so the C only has the function, and it's going to return a value, but sometimes you don't care about the value, and you just have the name of the function and it executes it, and in that argument list you may be returning some things. In Fortran, you have this thing call, a subroutine name, and it's expected there's no return that you do in an assignment. Okay, you'll see more about that. But the important thing that languages came up with, early languages, is the fact that they needed functions or these subroutines where you can put the code and you don't have to repeat that. If you didn't have the function call or the subroutine, you'd have to repeat all that stuff wherever you're using it within your code. And a subroutine or function allows you to package that up in some unit. And that's the part about programming in advanced programs, is this packaging up of things, putting them all together in some group. And basically, that's a subroutine, but that's not enough. We want to do things of packaging data together and using that data and actually having the subroutines associated with the data. Okay? And that's in C when you talk about a class. Did you talk about classes yesterday? Ooh, okay. Did you talk about structures? Yeah. Structures where they have start a structure name and they have a bunch of data in here in the main index. Okay, so that's a structure. Now what classes are in C is they just say, with this data here, I'm going to have these special functions to use. And so we're going to package that up. Well, in Fortran, we also do that with this thing called modules. And you'll see how that works in a little bit. Okay, so the old Fortran is not enough, and the Fortran 77 and C had flaws. The big flaw was that you couldn't allocate memory or ask for memory for the array on the fly in the code. You had to say, I wanted so much space up here in the beginning codes, and you have these arrays, and you say this array that has that can be indexed it can be indexed with index, or it can be accessed with the values within that array by index. That thing had to be set at the beginning. So if you wanted to change the size of that, you basically had to recompile. Horrible, you have to sit there with, I want a bigger size. I have to put these new values in for my array and recompile. Oh, that's horrible. It's terrible. So early Fortran, they thought, oh, I tell you what we do. We just make this thing called a common up here and this thing called an equivalence, and you can ask for all the memory, and then you just build your program working with chunks out of it. Oh, that's horrible, too. That's, it's just bad to work with. And so you find all these old codes with what they call these common arrays, common blocks, and it has all these values or arrays in there, and then depending upon what subroutine you're in, you can change the size of the arrays and things like that. And so it got really messy if you needed to change the value or the size of the arrays. You had this great big array, and you played games with making the array sizes bigger or smaller out of that. Horrible, horrible, horrible thing for it. So that's why we emphasize don't use the common and the equivalence. That's very, very, very old school. Okay, and so that was one of the problems. Plus, the way you had to write Fortran 77, you had to start in column 7. Ooh. And if you had to continue line, you had to put a sentinel, an ampersand, or a star in column 6. and then columns 1 through 5 were for numbering, so that you know where to use go-tos and things like that, where to end the do loop. It's just sort of a horrible thing to work with. I mean, you get used to it, and you learn how to read it, and that's good, but it's the modern way of doing it's much better. And everybody did things in uppercase. And I hate typing in uppercase. It's just horrible, hitting that cap locks and then typing. It's just, well, what about C? Well, C has its flaws too. Although you can do mallocs in C, you learned about doing that, getting space on the fly. You're in a code and you want to make an array, you do a malloc. And that gives you space for that array, but it's a pointer that points to that area of space. And you can use indexing in that, but now you have this thing, this pointer to work with. And then when you go to a subroutine, you have to have a pointer, and then there's this concept of aliasing as something else pointing to that, and it gets very confusing. So how many of you are C experts? We're pretty good in C. Okay, how many of you find, pointers a little bit hard to work with, right? Yeah, so they're hard. It'd be nice if we didn't have them. Well, that's what was nice about Fortran. So Fortran didn't have the pointers, but you had common blocks you couldn't allocate. So there were big problems with both of these. I mean, they weren't really big problems. They were with what we worked with at the time, and that was fine. But that's ancient, 1977. Some of you were not born, I'm sure. So if somebody's using 1977 language, you should just sort of, well, you need to modernize. Come on up to something a little bit in the future. Do I use it?
Or did you?
Yeah, I did. I used even before. I used Fortran 66, and so did that man over there.
Oh my God. Where's the older Fortran?
Yeah, Fortran 4 was even before that. So 19, I guess it was 19. Yeah, it started 54. We have a timeline to show you. It's just in there. So it started 54. I was using, I'm not going to tell you when I was born, but I was using it in 68. Yeah, it was in the last century, about 68, I guess. And so I was using, they used to have these things called Hollerith cards. So you just type your stuff on the screen right now. We had to go to what they call a key punch, and they had these cards that were this big, a key punch card. And you put your card in there, and you typed, and it made holes in there, the cards. And then that was one statement, one line. And you put all these together in a stack, and you took them to a card reader, and the card reader then ran your code, compiled it, and ran it there. It was all in it. We had a bunch of key punches in a room like this, and some operator who read the decks for you. And every once in a while, that operator would drop your deck. So you'd number the cards, or you would have the card deck like this, and you'd run a magic marker across it. So in case anybody dropped it, you can get those back in order. And if you made one mistake on that key punch, and you had big, 80, 70 characters on that line, you made one error on that, take the card out, rip it, throw it away. There was no fix for it. You couldn't backspace. And that was. You had to be very, 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 very precise. And you sat there, but as you got closer to the end, you went, okay, don't make a mistake, don't make a mistake. So that's what we went through. Okay, so using the language is important. It allows you to express thoughts in a more advanced concepts. If you know a more advanced way, if you know the advanced concepts, and it's actually maybe too plain or simple. So we have the basics, and then we have these flaws, and we have some sort of fixes with it, but that's not enough. And so what we need is the basics without the flaws, and then the advancement. And that's where we came, that's what happened in Fortran 90, 95, 2003. There's also 2008 that's out there. But most compilers are only doing the standard up to 2003. And the thing is, the concepts are very simple that we talked about. But the thing is it easy, really easy to use and learn the intricate things? And no. Actually, the important thing about these languages is that you want to do your science, and you don't want to become a computer science expert for doing your science. Maybe you want to become a computer science expert or somebody who's very adept at these languages, but the most important thing is for you to get your science done. And that's what this does. And that's why languages like Python are very popular. You can do simple things in Python very, very quickly. And so that's good to know. It's a good thing. But when you go scale up and you got to do the humongous calculation that may run an hour on 128 cores, then you need to think about doing things with not Python, but you need to think about doing things in parallel and using one of these languages, C++ or Fortran. Okay, so these concepts are easy that we talked about, but there are fine details that you have to worry about. There are rules and regulations. All this fine print is stuff you have to worry about. And then you have to do that, but then also conquering the math and making sure you did this right. You mapped those equations correctly into what's being done in the code. And as I was alluding to, when you go further on this, then you learn how to do things parallel. And your generation is the parallel generation. Okay, you're the guys who think who can do multitasking on computers. Now, if you're a guy, that's probably a little bit hard because it's that guys aren't too good at multitasking. I hope I'm going to get myself in trouble here. Girls are pretty good at it, but the important thing here is that to scale up, to do things, to work on these very large codes, they're all doing things in parallel, and they're using NPI, OpenMP, and CUDA. These are the two important ones up here that are being used to do things in parallel. And you'll learn a little bit about that. Okay. Now, with all those flaws, even simple things get to be very complicated. So if we remove those flaws and you start using Fortran 90, you're fine. Invest some time in doing this now, or thinking about and knowing some of the concepts, so that when you go to write a code later on, you have an idea how to organize it in a much more, quote, profound way than just putting little bitty pieces together, that you have a bigger feel for the structure of things. And so modern Fortran, that's what we're going to talk about this morning. It only took me, what, 15 minutes to get through the introduction, but I thought that was pretty important. So one of the things, it has a modern style of doing things. So I talked about how things had to be started in particular columns, and okay, move on. It has what they call free format, the modern Fortran. You don't have to start in a particular column with writing your code. The other thing that's really nice and explicit in Fortran, modern Fortran, is the attributes. We look at a variable, and that variable is going to be real, or it's going to be an integer, right? What type it is. We have to type it to know, because you can only do certain things with types, and you have to describe what you're using. And that's, of course, the hard thing with the language. But more than that, they have attributes that are associated with it. Things that say, oh, this variable can be allocated, okay? Or this array, we don't know the size of it yet, can be allocated on the fly. It can be private. It can be protected, or have these kind of things that are associated with it that's more than just describing its representation. It has attributes with it, okay? We'll see how to use that. And so that's a big thing. There's also this implicit none, but we'll talk about that later on. Just to give you a first review of that, is that in Fortran 77, the way things started out, and actually continues now, is that if you needed a variable and used a variable you would just say A equals 1 in your code down below. You didn't have to declare that a real value. When I said 1, what is that 1 going to put in there? Let's say 1.0. Let's say A equals 1.0. In Fortran, it would understand, because it begins with the character A through H, or O through Z, it's going to be a real number. Anything that you say I equals 1, J, K, L, M, or N equals 2, or something like that, it understands that that's going to be an integer. Okay? In your code, you just use the variable on the fly. If the compiler says, oh, I'm going to use these implicit rules in Fortran that if it starts with a I, J, K, L, N, N, it's going to be an integer, the variable name. Okay? And so it's like, oh, okay. And you thought, wow, this is pretty convenient. It's pretty convenient that you could do that. And if you follow that rule, you're going to be assured that, you know, everything's going to be okay. Because you run into problems there. And I'll show you a problem later on. We make it that fun. But it's better to say implicit none, where you have to type everything. Okay, where you have to be very explicit and say, this variable is going to be an integer, or it's going to be a real. And so you can turn off this implicit typing. And that's what that's all about. So lots of times at the top of the code, you'll see implicit none, which means every variable has to be declared, and we'll see some examples of this. Okay? Then the next, of course, is we have do loops. In Fortran, in C, you have for loops, right? C, for loops. In Fortran, they call them do loops. That's all. We have these nice things that let you exit out of the loop or just cycle once. And then we also have cases. We have this thing still, single and double precision, but we'll see how you use different ways to declare the representation of a number. So if you have a number, a real number, did in C you learn the different representations of a real number? Do you learn float and double, right? What's float? 4 bytes, right? And double is 8 bytes. Okay. So that's what they did up here in single and double. But the problem there, that's old school. What? Double of what? Single of what? So things, you know, and some of the older machines, it was 2 bytes. Or you could have 4 bytes, 8 bytes, or even 16 bytes. You know, and so what does double mean? Well, the modern Fortran said, we're going to get away from this. And so we'll see how that works. And so they fixed the flaws. We now have these things called derived types, which is very much like a structure in C. You know, there are these things that hold containers that hold different variables, right? Okay, and we'll show you how to use those. And if you didn't learn so much about them in C, the second time you're hitting it today will help you understand that. Okay. Then we have the modern oriented programming that has these what we call internal subroutines. Actually, I should say modules oriented. It has internal subroutines. You have the containers for the subroutines. And you were taught how to use a header file yesterday with C. A header file include something.h. Okay, that's what we're going to do with modules. We build our sort of fancy header files, these module things, and they can have actually subroutines in them. With build these modules, they can contain variables, and then they can contain subroutines. And then the subroutines are under contained. So you'll see how that works. And then we have these things called explicit interfaces. Then, of course, we have arrays, where, and for all, and we extended, you know, user-defined operators. You can have user-defined operators here. That helps in some situations. And we have special types of functions. We have functions that are built in called intrinsic functions, and then you have these things called elemental, which are basically vector functions. And we'll see how all this operates this morning as we go along. And then we have some mods and ends here. These are pretty cool. So inside your code, if you want to read, if you want to type something like a.out minus x is 1.0. These are arguments on your command line. And in C, did they show you how to get those? Well, we'll show you how to do that in Fortran. You can get in this code, you can determine that, oh, this is on the command line, and that has a value of 1 there. So you don't have to go in and change your code and recompile. You just read in a value. This might be n equals 500. You read in, and you get your value of 500. Okay. You learn about scripting. You could also in Fortran very easily do something like this: export n equals 500, and then just run your program. So from this, I get it from the command line. From this, I can get it from the environment variable, and I can just reset the environment variable, run it, or I can change the command line. Very, very useful when we're debugging things. Yes.
Which one uses less resources in the system?
I wouldn't worry about it. It's so minimal in terms of what these do and how much space. It's just sort of trivial. Okay. Yeah, it's one of those things you just way in the noise thing. Good question, and that's important in high performance computing. Is how much resource you're using. Resources in terms of how much compute time it takes, or how much memory it takes. And lots of times we make a trade-off between memory and compute time, and we'll see this in a little bit. You know, we might say, well, it'll take me less time if I use, well, it'll take me more time if I use less space, so maybe I should use more space and take less time. The important thing here is there's always trade-offs, and it's not just memory, it's also compute time, how much compute time it takes. And so the free format, here's an example of using the free format. There's a few things in there in Fortran. Number one is that you can start on in any column beginning with your statements. Here's our typical assignment. You can put more than one statement on a line, and you can separate these by semicolons. So that says, put that in the I, put 7 in the J. I can continue this on, or I could have put this on the next line. Okay, that's very convenient when you're doing something very simple and something, and it's easy to understand and for the user to read. Okay, and actually you could put in here. So if you're taking code from MATLAB, which ends in pretty much like Fortran, it ends in a semicolon, you can just leave those there. Not the perfect thing. Okay, so we make assignments here. Continuation is done by putting an ampersand as the last value. And so this is a continuation. This line is a continuation of that. You take that out and put that up there, and that's the same thing. Comments or an exclamation point, or in Unix, people call that a bang. So here's a bang, here's a comment, assignment, multiple assignments, or multiple statements on a single line, continuation, program up here, and then we usually have an end in Fortran for things. So in C, you usually have this concept of a block. You have something up here, a squiggle bracket, another squiggle bracket, and that's the scoping for whatever that block is right there. In Fortran, you usually have to have a start for something and an end. So we have a program begin and a program end instead of having a main squiggle and an end squiggle down here. Okay, no problem about that. And some of the snippets of code in here, we do not have the end value here because in trying to keep things short and fit into these spaces, we may not have that. We may have dropped that. So, yeah. Actually, in Fortran 2003, and people don't use it, they have that. It's not a squiggle, but I think it's a block start and block end, something like that. I'm embarrassed to say I don't recall what it is, but in the new part, they have a block that you can use for scoping. And I forget what it is. I'll find out. Any other questions? Okay. More advanced things? Okay. Good code, bad code? Well, it's not so bad, but it's a little bit hard to read. So here's the old code, Fortran 77. You started in column 7. You'd have a program start, and this is not using your spaces. And over here, there's better way to do that. Make things readable for your user and yourself. Believe it or not, do this. You write a code, and even though you may not use it 6 months later, go back and look at it and say, can I read this now? Does this make sense? Because after 6 months, you sort of forget. And so number one, you need comments, and number two, you need it to be organized in a way that makes it clean to read. And using spaces between things liberally helps that. Okay. And you have terminals, and you have these big screens now, so you can easily scroll down. Okay. So in Fortran, this implicit none says I'm going to specify the type of every variable I'm going to use someplace over here. Note over here, I didn't. And what happens here is it's going to say, the compiler is going to say, that is going to be a real, because it doesn't start with IJKLMN or N. And then it says, okay, here's what I do here, and here's an if statement. And over here on the Fortran side, I say these are variables that are going to be real. And in Fortran, the default is going to be 4. When they say real, that's 4 bytes. So that's like a float in C. It's 4 bytes in terms of the representation. Okay? And here we have our start and end down here as usual. And as I said, the implicit none. So blanks, blank lines, and comments are your friends for reading and making things look good later on, so you can visually quickly understand sort of the structure of things in here. Okay, a little bit more. So now let's go to the do loops. And you used to have to do loops this way, where you would have the do loop. You'd say do and go down to 100, which is down here, and these columns over here were reserved for these numbers over here. And then what's bad is if you were using 100, 101, 102, and then later on you had to put something in the middle, it's like, okay, do I go back and rename all these, or what? Or do I put 110? And so it just got sort of messy. And what they did was get away from that. There's a do loop over here. It starts with the do. And as we said in Fortran, you got to end it someplace, and so you can do end do. And you can have a space there or not. It doesn't make any difference. So here, what we do more modern is to say we have an integer. That's what's happening up here. We do I 1 through 20 down to here. And that integer I is going to be changing values in this do loop from 1 to 20. And what I'm going to do is take this and to make it into a real and shove it into, take that integer, make it real, and shove it into x. And this is what I'm going to do. I'm going to multiply those two values to get the x squared, and then I'm going to check to see if it's 13. And of course, it shouldn't be 13. Yes?
I have a question about that.
Yeah.
It's really easy to see the do 100 and a 100 continuation, see that's a loop.
Yeah.
And if I had multiple do loops, it would be really easy to see how they're nested, if there's loops within loops.
Yeah.
Over here, the end do and the do, you don't know how they hook together. Which end do is that?
You can put a comment here and say that's the end, but usually what you do is indent. And so lots of times Fortran up here, and these guys, you'd have a 200 here, or maybe a do 200 up here. And then the question is, all of a sudden you'd see these endings, 100, 120, 200. Here, and that's what we're saying, you indent a level. It's just like in C. You have 4, and you look at 4, the top outer 4s here, and you indent the inner 4 here. Well, you do the same thing up here. That's pretty nice. If you had a do I 1 to 20, and then under that you had a do J 1 to 20, you would start the do J here. You would end all this stuff. This would be your outer end, and then right here you would have your inner end. Okay, and so that's how you would do it. And so in C, they teach you to do this. In Fortran, because of the way things were done here, when they got modern, people just kept keeping it flat, and that's bad. You need to see the structure, like David was saying. That helps a whole lot if you can discern, here's a do loop here, and you can put a comment here if you want. And that's done in C quite a bit too. Yep.
Chat is on here. Apparently.
Okay. 10:30 sound okay for a break? Sort of late. Or you can just go back and get yourself some coffee. Especially with a language, when you're learning a language. I need to stay awake, okay. Okay, questions? Okay. Now we start getting in, that was sort of the basic stuff, and now let's get into sort of the attributes for this. So at some point, I'm going to need arrays, and in C, you just said it's going to be real, and then you might have A with the square brackets 100 or something like that. And in, whoa.
Sorry. I didn't mean to stop you.
Well, I forgot where I was. Well, I need the attributes part there. I'll get some coffee. Yeah. How about if I just go? Are we back already?
You can just take a quick break. Just 3 seconds.
Yeah,
Jason,
3 seconds. I'm gonna get some real
send me a
coffee.
message again. We're just going to take a coffee break for just a second. Can you do that again, Jason?
Yeah. We did it everything. And that's why it was so good. Yeah, we usually did everything. I did take care of it. And then I put all
I close this. Just not close the Hangout. Now logged in is. It's coming. Send another message.
Yeah. That's what I got.
Give me another one.
So, okay. So you guys should ask questions. Don't feel, you know, if you don't understand something or we can slow down. We do not have to finish our slides. Okay. So just got any type of question, just hit me with it. And in particular, if it's
Go ahead, try again.
well, if it's small or even if it's large in terms of the scope.
All right.
Okay, let's see. No problem. We're back to, oh, okay. So I'll start talking louder now because middle of the morning and you keep going. So now what we're going to do is introduce the attributes. And one of the things is how big is these arrays going to be and how do we designate that in Fortran? There are different ways to do this. This is probably the quote standard way to start doing this, but you'll see other methods. So you declare what things are here. In Fortran's modern Fortran, you have a variable list over here that's going to be integer, and that's separated by the double colon. Okay. Now, actually, you don't even have to stand the old method. You didn't have this double colon, and that would work if you didn't put that there. But this makes it easier to read if you have something separating the specifications over here with actually the variable names over here. If you line it up like this, and somebody can just run down that list and have a good feeling of the way things are. Usually group integers and reals together like this, very handy. And so if I'm going to specify I have two integers, ij here, a real, those are both 4 bytes. Okay. Here I'm going to say real, this is going to be a parameter, And if I have a parameter, I do put a value there. Since it's real, this is 4 bytes, the representation. So this actually can extend out some more digits, accuracy about 7 digits there. And what happens when the compiler is running, it says this is a parameter. If I see pi anyplace, I'm going to stick it in the code right there, and now I'm going to compile it. Okay? It's like a macro in C. Okay, you went through macros yesterday? No? Okay. Oh, but this is cool. It says any place I see this pi here, I'm going to substitute that value before I begin compiling it. Okay, so that's what it does. This is how you specify the dimension of an array, right here. You say that it's going to be, this thing's going to be a real, and by saying dimension, you say it's going to have an array, and this is going to have size 100. You could actually not use this and put the 100 over there. That's okay too. You see that. But the standard says, oh, okay, you do this as if you want to use the attributes to its fullest extent, you put the dimensions and things like that over here. These are the standard, just the default for in terms of how that variable is going to be represented into real, and then with the attributes, it's on a separated list here. Now, this is the more modern stuff. This line down here, and this is when you do need to use a dimension, is it says this is going to be 2-dimensional. Here's one of my dimensions right here, separated by a comma for the other dimension, and that colon means I haven't decided what these are going to be yet. Okay, that's what that means. And this says it's allocatable, which means I don't know what the dimensions are, but later I'm going to allocate the space for this in my program. Woohoo! Fortran 90. So there you go, and that's dimensional array, 2 dimensions. Here's the syntax here. Not that important because you'll come back and find out. And if you forget, you'll remember later on by coming back to these slides. We do parameters, dimensions, allocations. We'll see intent for subroutines. We can actually have pointers and things pointed to. Don't use that much. We can specify this should probably be with intent and subroutines about whether an option in the subroutine argument list is optional or not. And then we can use these things, which we'll see are more important in derived types a little bit later, and in modules. Okay, so that's the first beginning step. You saw the implicit none, where we say that what we're going to do now, and here's a statement that you can go back to later on, the I, J, K's, L, M, M, N's as default. If it begins with this as integers and all other variables real, all bets are off there. You have to describe every variable in terms of what its representation is going to be. Okay, doing loops. Now that we don't have to use the value, say 100 here and 100 down here to indicate the beginning and the end, here's the syntax for this. You start off with 1 and go all the way up to n, up to this value 100, and this says you can have a stride. Okay, that's easy. That's a lot easier in C to be able to put that in. It's very direct right there. It says, oh, if I want to stride by 2 or 1 in terms of this index, that's the way you do it. We now have the while loop. Start off a value here, and it's called do while some value here is going to be evaluated through every iteration of the loop. And here I'm just incrementing that value, and this will go through it 20 times. Okay, yes?
Why do you have it at first I equals 0? Because the minute I always be less than 27.
Well, the initial value here, when it comes out, when I'm right here, and I say, is I greater than 20? Or should that be less? Oh, wow. While I is, this should actually be less.
Oh, okay.
So, yeah, I did these late the other night. So while I is less than 20, but you have to have an initial value, here's where you increment here. Good, thank you. I'll correct that.
That was a test.
Yeah, I was a test. Yeah, just seeing if you're awake. I wasn't when I did this.
You did that for
Yes, I did that on purpose. That's yeah. Okay. And then the same thing over here is, and then so over here this is correct. So if I is greater than 20. So here and in C you had these certain constructs you can use to not use a index as you're going through things, which imply a limit at the end. Here, there's no limit at the end. Up here, there is. There's this 100. Down here, for a while, it just is under this condition. And then what's nice here, this is sort of, you'll see this, is this says just keep going. I don't care what. So if I didn't have this statement, I'd just sit there and spin, you know, to infinity or till you control the program. Nice thing here is for these particular types of loops, infinite loops, or repeat loop, you can exit out of them. Okay, and that exit can if evaluation can be any place in here, as we show in the next slide. Here we have a do loop up here, and we exit in the middle, someplace for some condition. And so when we do exit, you have to remember these values will have been evaluated, and this says when I is greater than 20, exit. So at 21, these will have whatever this is up here, and this will only have been evaluated for 20 or whatever it was. So you have to remember that if you jump out in the middle someplace. Another thing that you can do in iterations, through this, we're going through this, you can say just cycle through. This says if I reach over 21, just come down here, it'll come back over, and it'll do 22, and it will say, and it will just go around this part for all values up to 100, but it will have stopped doing that part of the loop for values less than 20. 21. Yes, for 20. Okay, and so we have the exit that can appear any place, the cycle to skip to the end. So this says completely get out. This says, oh, don't do the rest of this, just hit down to the end, or maybe, oh yeah, here and go back up around there. And it works with routines that are bounded or not bounded, you know, with the do or the do I equals 1 through something. Okay. Another thing you can do in Fortran 90 is you can label statements. This is a label for this statement up here. This is a label for this statement down here. And you can also specify that this is the end of the inner. Okay? This is the end of the outer. You do not have to use these, but of course, here's the important thing up here. And this says when we're finished here, don't exit just out of the inner. This says go ahead and exit out of the outer. So that's why they had the naming convention there. So if you have nested loops, you have someplace to exit to. And here, I could have put that as inner, or I could have put that as outer. When I say outer, that's going to go all the way around. Likewise, with the cycle over here, I can do the cycle in terms of going to that designated or named statement up here. So that's, and you'll see this naming down here of things. So you can do an end, you can have a program, say, what we call our program program John, and at the end of the program you can just have an end statement, or you end program, or you can have end program John. Okay, so this is sort of typical that you might end, you know, have these end loops labeled here, and you can have this well, you have these loops labeled here, and you can have the label also at the end. Okay, we also have case in Fortran, just like C, and these are integers or characters in here, and this says I have a case. I'm going to set a temperature to some value someplace in here. Here it's going to be an integer, and then down here I start with my case and end the select. So I start, select, end select, and then I have the different cases here. And so if my temperature, and this specifies a range, this says from anything below 1, that's anything here up to minus, well, anything over here up to -1. So when you see a colon someplace like that, the colon means there's some starting and some ending point. And you see that in array reference. And up here are a reference like this. And this says any value here, because I didn't put anything, any value less than this, or wherever things, wherever this might start, up to -1. So this is minus infinity up to -1. This says if I'm at 0, I'm freezing. If I'm at 1 to 20 for this integer, then it's cool. If I'm at 21 to 33 Celsius, it's getting warm, and then I've got to be in Texas if it's above 34. That's in the hundreds someplace, I guess. Yeah. Okay. Okay. Now to talk about declaration of variable sizes with their particular representation. So when we say that something's real up here, that's 4 bytes. Okay. And what we may do in our code, depending upon the computer, we want to assure that that's either 4 bytes or 8 bytes. And we have to be able to talk about that a certain way. And that is in the number of digits of accuracy. So here, I don't know, it looks like I have about 15 digits here of accuracy. And that's for a double or 8-byte representation. If I have a 4-byte representation, that I only get about 7 digits there. Okay, so 4 bytes you're going to get about 7 digits representation. 8 bytes you're going to get about 16. Okay, now depending upon how that's represented for that particular machine, 8 bytes may only give you 13 digits accuracy, or it may give you 16, say someplace between 13 and 16 for that. And so, okay, you have 8 bytes, but the important part in a calculation is that you want so many digits represented. So many, you know, you might need 15, 13, that's fine, that's sort of 8 bytes someplace in there, or 7 bytes. But how do you say this to the compiler, and how do you express this? And so we're used to seeing things like you say float in C or double, and that's 4 bytes or 8 bytes representation. And on that machine, actually, you know, you might have to settle with 14 or 13 digits accuracy in how they represent it, or you might get 6. And so the big thing here is how do you have a more advanced method of doing this? And so the way to do it is to actually specify this thing in Fortran called a kind. Okay, and the kind here can be a number, or it can be a parameter that we set. And what I'm going to show you here is the mechanism for doing that. So the mechanism to do this in Fortran is to say, I'm going to have an integer. It's going to be a parameter, which means it's going to be substituted throughout the code wherever I use it from the beginning. You know, it just goes and substitutes that in the code first, and then it compiles it. And colon means here's my statement over here with my attributes. This says, here's that value, and then this thing says selected real kind 9. And in Fortran, this is special. This function here is evaluated before it really compiles the program. It's one of the few functions that are done like that. It's evaluated before anything else happens. It will run this function right here. It will put this value here, and then it will take this value and put it wherever it needs it, in particular in statements that you specify for things to be real. Yes?
Is that like a type of construct?
Yeah, sort of like typedef. But actually, it's something that you can have a value in here, and it's going to figure that out, okay, for you. So what's happening up here is, if we're coming down into the code, and I just declare this real, I can specify, there's a function that says I got an I, and I want the kind of that, and I want the kind for R up here. So I and R up here. And this is integer and real, and it says 4. And why would it say 4? Why would they use the type, why would they use the number 4? Because reals and integers are 4 bytes. So it makes sense that all the vendors would say, oh, 4 is going to be the value I use for that kind to represent 4 bytes. A lot of work just to, say that. But actually the standard says you can use any number there. But most vendors, if you do real or integer here, the kind is going to be 4. If you did wanted these to be 8, and you'll see how you do that, other ways to do that, it would say the kind is 8. Kind is 8. You could actually say double precision, : R, and then this would be 8 here. Okay. But what this thing does right here is that it says, I want the real kind with 15 digits accuracy. So that will return usually an 8 over here. Whatever that value needs to be to get 15 digits accuracy. Okay, I could have said 13 and say, oh, the minimum is 13, I got 15 for this particular machine, so that's okay. So you might see 13, 14, 15, or 16 here. But some machines will have, it'll be 15, so it will try and even go to a bigger precision than double or 8 bytes, so it'll try and use 16. And usually that's incredibly slow, so you have to be careful. So that's why you'll see lots of people just put the minimum here, say 13 or 14, and then they're happy with what they get. That's going to be 8 bytes. Okay. So all this stuff says here, the easy way, the difficult way, but the more modern way to do this is use a selected real kind or selected integer kind here to specify. And I use this nomenclature right here. It says kind real 8 bytes. That's what I'm looking for. I put it in terms of the bytes because, you're happy with 13, 14, 15, or 16. And so I'll put, actually, that would not work. That should be 13. That was another quiz, another check right there. That should be 13 or 14, and then this will work right. Okay. So, and if I did this, this would be a 4 value. This would be kind equals 4, and that would only be real with 4 bytes. So this needs to be 13 up there. Okay. And yeah, I don't know why that was. Oh, that was labeled. Yeah. So I would actually, if I were to do this right, I'll go back and do this. That's kind real 4, kind real 4, and that would work. No, wait a minute. No, I'm sorry. 7 bytes or 7 digits accuracy is 4. 7, 8, and I guess 8, 9 would start you out on the double. Yeah, because these numbers up to about 7 is single precision or 4 bytes. It's actually 8, 9, 10, 11, 12, 13. I usually put 13 up here. I don't, because there's a little bit of fudge down here, but actually 9 should work. And that will give me, that should be an 8 here, kind real 8. Oh, sorry about that. Maybe I should drink a little bit more coffee here. Okay. Okay, so here's an explanation, a little bit more of an explanation of that down here. Here's another way of doing things, and you'll see a lot of code still doing this. This says real, and I want whatever representation is 8 bytes. I want whatever representation is 4 bytes. So real star 8 and real star, say 4 down here, are describing the representation and number of the bytes I need, which makes much, much more sense. And I think they could have made actually the interface a little bit cleaner on Fortran, but that's what you have to live with. Here's how you do it in the modern Fortran, is you say it's kind 8, but you have to say it's not completely safe, and so that's why we do that function call to make sure we're in the right, we're using the right numbers there. But you will see this in some codes that they just say kind 8, and most of the vendors do that, but it's not absolutely guaranteed. Okay, and here I can get an integer 8, so a 32-bit or 4-byte real can only get you up to 2 billion in terms of the integer value. If you need to go past that, then you need to use integer 8. And there are times when you do that. If you want to specify a constant here, you can use the size it's supposed to be. You can represent it as a _8 here for the number of bytes. This looks sort of strange, and so that's why I don't like using that. If you saw _KR8 or KR4, you know it's kind real 4. That's a lot cleaner. This is just looks difficult to read. So I'd suggest you doing what we did before, but you'll see some of this sometimes. So I like doing it a different way. So if the standard says, if you put here E0.0, you've sort of seen that, that's in C, you see that, that means it's going to be a real 4 byte. If you put D0.0, that means it's going to be, quote, double precision, or it's going to be 8 bytes. So I usually make this that way. So if you, and the default is it's only 4. So if I had this number, if I put pi here out to 15 places, just 15 places here, and stuck it into that real value over here, that's 8 up here, that's 8 bytes, but I had this, and I had this over to 15 digits over here, it would truncate it to 7, because by default, all constants are just real 4 bytes, and if it sees that, it will truncate it to 7, and then put that value over there, so you get a truncated value. The way to get around that is to put, let's say, 15 values, 15 digits here, put an _8, kind real 8, or a D 0.0, and you will make sure that the compiler understands that this constant over on the right that it's evaluating will be evaluated at 8 bytes and then put over here. So that's what happens in constants. Constant by default is only real *4 or 4 bytes. Okay, that's an important thing to understand when you're really worried about the precisions in your code. So we have some codes here that are really worried, and I really take great efforts to make sure that their accuracy is about 14 digits. And I had one code that they changed a parameter one time, and the person called up the next day and said, look, my calculations are wrong now. What do you mean they're wrong? He says they're off by 1 digit. and that happened because in the code, this is a code that was distributed, they had changed a parameter, and they made the announcement that he didn't read the announcement. So it wasn't really wrong, but it was off this. But some of these guys are watching out because they're taking differences of large numbers that need this accuracy. And so there's the different ways you'll see this in Fortran. And you'll also see how to set these. This is truncated over here, but it's only 4 values, digits over there, so it really doesn't matter. This is the more modern way of doing it. You say that if I have an integer, I make it a real, and then put it over into this real. And then the older way was to work with doubles and say this was I'm going to make this a double, and put it over there. And this says the newer way, I'm going to make real I, and if it's not the default, which is 4, make it kind 8, or KR8 over here. Okay, yeah, that's the nitty-gritty sort of the details that you can get hung up on, and so we're going to get away from that. Good, away from those. I hate so much detail. So let's talk about allocatable arrays, and then let's go ahead and take a break after that. So we are going to look at how these allocatable arrays are being done. So when you make space for things and when you're running a code, it's put on this thing called the heap, and that heap has lots and lots of memory space associated with it. By default, if you just have an array value and you hard code that number and you don't do an allocate, then that goes on the stack, and the stack is limited in size. And actually, the thing is the way they are in memory is you have all this memory for whatever code you're running, and I think the stack increases upward and the heap increases downward like that, and they don't meet in the middle. And the place where they do meet is a low value for the stack. So if you try and compile a code and you have arrays in there that are hard-coded with sizes, and you get either a compile time error, or you might even get a runtime error, try changing that to an allocatable array and see if it works. And there are also compiler options for changing the size of the stack that it will allow. So, but you have to be a little bit careful if you do the old style and make these static arrays one value, a large value to begin with. You might run into problems. Go read the documentation on how to extend that. Okay, it's better just to make allocatable arrays and allocate them at the beginning. And then we're going to look at structures and derived types here. And so allocatable arrays. As we discussed before, you have to, if it's going to be allocatable, you have to specify the shape of it. And this says, I don't know what the shape, it'll have some starting value here and some ending value, or just a size value. So in Fortran, everything starts at 1. Array indices for array indices. In C, it starts at 0. Big change, difference between the two languages. Always starts at 1. But you could start your arrays at 0 later, and I'll show you how to do that later on. Or if you could specify, if you want, if this wasn't allocatable up here, you can say 0 to 100 or 0 to 99. You would have 100 elements, and you could do the indexing just like at C, and start your do loop at 0 and go to 99. Okay, so you can take C code and change things around and put it in your Fortran if you want. I don't think anybody in here is going to do that. But I do for different classes. I'll have the C and the Fortran version side by side for things when we teach parallel computing. And it's sort of interesting. Anyway, this is going to be two-dimensional array. We haven't specified the size, but we specify the shape, two-dimensional, separated by a comma here. It's allocatable. Here's how we do it. Down here, I do a read. This is another way to get something from the line. So here's read star, comma in, comma in. And so I would just do something like this, where I have a dot out, and read in, say, a file called X, and if I cat X in there, it might have 100 and 200. So this is another way to get values from a file. It's just do a redirection here. This defaults to, note, I do not have implicit none here. So what it's going to do is default to integers here, and it's going to read those as two separate lines from some file. So you know how to get things on the command line as arguments. You know how to get it in the environment variables. You also know how to get it just from a file. So pretty neat. Here I'm going to allocate it, and I'm going to specify the size, and that's how you do it. The array with the size. Here's a two-dimensional array. It's going to be n by n, and then you can get an error status on that. Was it able to get the allocation? That's always helpful, but sometimes when you're in a hurry, you go, you don't have to use this. This is one of those optional arguments, and usually the status is going to be put in IError, and then you test that value. If it's not going to be 0, you know something went wrong. Sometimes we have codes that get way down that have lots and lots of 150,000 lines of code, and something goes wrong someplace, and we always advise them when it looks like it's happening someplace with allocation to go ahead and get the status of things and evaluate that status. Yes?
You have to specify allocatable, like you had to mention, specify what the dimension.
I think you do. I have not tried that without it, but there's a way. You'll see in subroutines, we do have this, and it means something else. But right here, I would always say, always put allocatable if you're going to allocate it. I honestly don't. I've never ever tried not doing that in the main program. Okay, good point. But I think you have to have allocatable. I have to go try that at lunchtime. Okay, and then when you're all finished with it, you can deallocate it here. And of course, we don't have the in program down here because we're running out of space next down here. So, and you don't have to specify the size in there. You just have to specify the array or that thing that you allocated. And you'll see this in codes. A guy will start and he'll say, I want a bunch of space for this, and then he'll do it. It may even be scratch space. He needs to let it go, and then he may allocate space later on. Lots of times, and you'll see that in codes, lots of times you'll see at the very beginning things are allocatable. They read something, how big it's going to be. They do all the allocation up front, and that's okay. But there are a reasonable number of codes that allocate in the middle. And of course, that's always hard to say, because if you try and allocate in the middle and you're over your memory limit, then it's going to just die, you know. And so it's always good to allocate if you can right in the beginning, so you know, so you're not going to run your code for 2 hours and then need a little bit more space and it dies. And that's a typical problem. People do that. And so we, you know, let's say, hey, try reducing the size of your code, rerun it, and see if it works now, you know. And so that's good. So why don't we come back for the structures? Let's all take a break, a little bit of break, and we're going to talk about these things: structure or drive. We call them drive types at Fortran. And I'm going to go back to. I may go try that problem we were looking at with without saying allocatable. I bet you the compiler doesn't let you do it. So let's go ahead and take a 10-minute break. Come back at 10:30 and continue. And any questions?
Are we gonna do like start buzzing with this in the afternoon section?
I don't think so, but I can make available some test codes I did. I was running on this because I found that whenever you lecture, you know, you change things around a little bit. And so the bottom line is when you, before you lecture, whatever's there, you always copy it, paste it into a file, and try compiling it and running it. And lots of times you'll find errors. I can make these available, and there was no lab, but we don't have a lab for this at this point, but I can make those ready. So, but you guys, have you been on the machine? Why don't you untarget a file?
Yeah, they did some originally.
Okay. I have some. They're not guaranteed. They're just these things I cut and paste. You can try different things. I'll put those in a tar file, but I'm not going to tell anybody but you about them because they're incredibly quick. They weren't like this. So why don't I go tar those up and put those in an area where you can access them, and maybe we'll cut off at 11. Yeah, we're not going to make it. Yeah, maybe you can do that this afternoon. Yeah, you have 10 weeks here, right? Yeah, maybe we'll do that this afternoon. Okay, let me go get that ready, and we'll come back in 10 minutes.
Would you like to share it?
Absolutely.
We discovered the music with flies. We wanted to be here with new tracks.
Another thing it says, because I'm just pulling it up from
And what's one thing?
Yeah, no, it says API and P, but that's all.
This session. You can do this on and the systems in actual
It's so realistic. It's like when you're a kid, it's like, this is so stupid. Spaghetti, and then spaghetti. That's so lucky. I like certain stuff. I've seen it. Okay, well, no, have you seen?
What do you do? Just figure out what's going on with those characters. Still does that.
Sorry. If you talk to your guys, I know, there's things that like pass on for everyone. It's a wonder why we're not all everything. I think that's a problem where, like, oh, you said it's really well.
Shredded. It's a sweet. Yeah, try not to do it. It's just kind of
yeah, that's why I bought the people. Otherwise, people would run their out. I think that one is that but there's two that you're not
like IKEA.
But there's about like if you have some really long file.
I just stuck heat sort of thing.
Well, I don't know.
Like not Tiber. It's just snap.
No, laziness is the greatest.
It works. Yeah, there's buttons.
If you run the matches, all right. So.
Can I easily get a terminal? No, why don't I just do it over here? Now, this, I can put it on the board, and that will work. So, you want the files? I just stuck them there, and I'm going to remove them very quickly later on because they're not professional. And so here's how you can get a hold of them. And so you've had Unix course on that. How many guys know Unix pretty well? Linux, Unix? Okay, so here's how you can once you're on a Stampede login or node, that's all you have to do is the tar command, and the command is tar -x -l. You can put the minus there or not. It's not really difference. The X means extract, the B means verbose, and this says the file to extract it. Okay, so that's what that command means. That's old school. And then you're going to go to, this means tilde train. That means go to the directory, that means the directory of train, home directory. So that's just going to do that. And there's a file called Fortran codes. I'll try that. I think it is _.tar. And yes, pretty sure that's try that. And it should then, you'll get a directory folder called Fortran codes. And in there there'll be some things and then they're called something similar to what they're about. Precision. Yes, the square root thingy. And I was just checking things there. I pulled the code over and made them sort of, well, work. So, but I had no intention of getting to you in this mode, but I think it might be helpful. You can pull up one of those things.
iPort is the
point. Yeah, to compile these, just port and then X dot F9 for this the main code.
And just a reminder to everybody, again, you can compile on the login nodes, but don't run the executable.
And actually, don't listen to this. You can do this on the login. It's just a fraction. That's the official rule. You know how to get to the backend nodes?
Yeah. What is submitted attached?
You submit it back, but how do you get over there and interact with it? Huh?
I just noticed. I know. Kill one side of it.
I know. Because I wrote it. I did. Just type, and I'll get you to a backend node. Development. It's really handy, so you don't interfere with people on the login. But these codes are so short that I think in this case, no problem. The longest they do in time is, milliseconds. And I know your user services, you have to make sure everybody obeys, but I hope you guys can try. You can point to me. Okay. I'll take the heat. That's okay. So let's see. So you compile it, you run it, and of course it will make it a.out, right? A.out. And the executable called a.out. Do you know why they call it a.out?
Trick question.
Yeah, that was a trick question. Do you know?
I think it just assigns a random character.
It's the first one. They used to call output on something, and so in our courses, I say an executable, whatever, we're just going to call it a.out, you know, and so you know. Because if you, that's the default.
If they just put like the name of the executable in front of that,
Mhm.
it'll output it to that, and then the file is out.
Yeah. Okay. Oh, okay, so the next important part is we know about allocatable arrays and how to do that now, so you can get that anytime. That's a big thing, free format. And now we're going to go to the structures, or what they call derived type, and that's where you have this package here of different variables in there. You can put all your parameters in there if you want, or whatever. It's probably not so much used for parameters as it is for variables, and not even so much variables as it is holding different arrays. Well, actually, that's it's reasonably important for holding just scalars and arrays. And so here, I'm going to name this thing called myStruct, and it's going to have a beginning and an end, as usual in Fortran. We're going to have some integer in there, some scalar values here. One's just 4 bytes, the other one's going to be 8 bytes, old school way of doing it. That works, you still see it a lot of ways. We're going to have an array that's going to go on a stack, 100 by 100 here, and it's going to be called S array for stack array. And then here's, we're going to have one that's allocatable. And yes, I tried not doing that, and the compiler warned me. It said, oh, you either got to make this a pointer or allocatable or something. So yeah, you cannot leave that off if you're going to use it for allocation. And then down here, we can also have other types in here. And this says we're going to have a type, and someplace else we called it other struct. And actually, this structure itself is going to have a dimension of 5. And we're going to have a type within a type. And that's okay. You don't see that too often. Generally, you just see things that have types and they have these structures, and they have information that's passed around from subroutine to subroutine. Here's an example of how that's to be used. You have your type declaration that we had up here before. Here's our program, in program. Here we had our program name up here, and we could optionally include that down here. So that's sort of standard in Fortran. And then here we have our declaration of our types that we're going to use. So before we said, here it is, I'm going to have all these variables. And now here I'm stating, usual Fortran way, not real or something, but I'm saying a type that I make. That's why they call them derived types, because I derive it from other intrinsic and standard variables and group it into this thing called the derived type. And so we have our type, we name what that type is here, and that's going to be called data. And so I get to use what's in there. And then here we have an array of those types. Okay? Lots of times you just see this. Occasionally you do see where we have an array of these things, and we're going to show an example of using both in this next one. And so here, and this is, you see this in C++, and that's why it was written this way, not so much a HPC type of code you would use, but it's related very much to what you might see in C++. And so up here I have a program name, I have my types, a type that I have called a person, and in this person type I'm going to have a name. And for, if it's a character, this says the length of the character string is going to be 10. So I have to be careful with this that the name's not more than 10. How to handle variable lengths is another problem, but we're not going to discuss that. For simplicity, we're just going to say, oh, it's going to be 10 or less. And in here, I have the age in a real, as a real value. I could have made it integer, but of course, age changes, so you might need a decimal point and make it real. And in here, I have a electronic ID that's associated with the person that's the ID. Here, again, inside the code, I have that type declaration, And I want just one over here, one derived scalar type structure, scalar meaning only one of them. And then here I'm going to have an array of these guys called we. And it's the size is going to be 10. And here's how you access things. Yes?
Is this what, you said Fortran doesn't have classes, is this?
Fortran actually does have classes. I don't think, I didn't
Or you
allude
said
to.
they're called modules.
They're called, well, the classes, it's something we have that's quite similar. We do have classes, okay. Something that's very akin to the C structure is this derived type, okay. Now,
So like, what is this? This one looks like classes,
we're getting close to it, and you're thinking right. That's good. So the way you make a class in C and C++ is that you make a structure, and that has all these things in here. This is a derived type, and that's why we call it a structure. It's a derived type. And in C, C++, you add functions to those, or methods, right? Okay, we're going to get there in a little bit. We're going to do that in something called a module here. Okay, it's very similar and quite usable in that regard. Now, in Fortran, and we're not going to cover it because it's a little bit more complicated, there are classes that use pretty much that structure, but we're not going to talk about that. And so you hit it right on the head. This is very similar to C, a structure in C, and a structure, and then what C++ is, they just took the structures in C and they added methods to it, function calls, and they call that a class. Okay. And what we're going to do here is show how that's sort of done in a module. And we'll see that in a little bit. And then you can call those classes. But we're not going to talk that way because we're just going to provide some simple things here. Very similar to your class in C++. Okay, but the first thing we got to start out with is structure, how those behave, how you get at information inside that structure or derived type. Okay, I see you going, ugh. Okay. So what's, hit me with some words what you don't understand or you're thinking about, or where the confusion is.
Maybe, I don't know, I've been hardwired to process eventually not functions and stuff. So if they're not doing that, they're not doing this to create methods or functions.
Yeah.
They're just defining a bunch of data.
Yes, that's right. And we put them in this thing, in a group. And that's the basic idea. The very, very basis of a class is at the top, right? You have all these variables. And that's what we're doing here, first off.
Yeah, that's what I was thinking of.
Yeah.
So I'm saying, if you're doing that, what do you want to do with them? Why specifically set it up like this? Why don't you just create a bunch of
Why don't I do the whole thing at first? Yeah, I'm not going to go with the whole thing at first. And there's a reason we do it this way, because in C, you don't have classes, right? In C, you only have structures. And that's why we have lots and lots of people that learn just C first, not C++ or Java, things like that. And so you guys already know about classes, and you just have to bear with me a little bit on this. And say, oh, yeah, I don't see how you could use it. Believe me, you can actually use this pretty well. You can use derived types.
I'm just thinking because it looks like it might be easier just to create variables. Or I guess.
Yeah, you could, and people do that. But the thing is, if you want an array of these, and it's right here that we sort of come to this, you put this. We now have an array over here. The old way, if we use these someplace else, we would have to put an array of called names, an array of A's, an array of IDs, and we can just keep those. And the first one has a name and you could do that. A more advanced level is to make a structure out of this and an array of those structures. And now when we do that, we just pass it as we. So this is probably the thing you might have skipped over when you're learning C++, is just sort of the functionality, base functionality of doing this. But stick with me and you'll see how this is. Yeah, we're getting there. Well, and here's how you get at that. So this is the declaration up here, and in Fortran, if we have this derived type or structure, now if we're trying to put those values in there, we have something called name, age, and the ID. And down here, we declared this thing, this structure, as U, and now we're going to put some values in there. So we take U, and this is like the dot in the structure for C, and this, we use a percent here, and this says the structure U, the element inside there called name, we want to put John Doe in there. We use that as to get to the element in the structure. Here we're going to put our age is 34.2 to we, and then we're going to put this ID as the element in there. So no, that's not. That's an assignment, and that's an assignment in a structure. Yeah, we're getting to where you want to go. Just hang on a bit. We're going to get there. Okay. But we want to go from this ground that some people haven't had classes before. Haven't had classes in C++. So let's yeah, if you can bear with me, we'll get there. But very good points about this. Why are we doing this? And we're building up, and there's usability in this sense that we can name a structure. It has a bunch of objects in there, and when we go to pass it around, we can just pass it into a function call here. That's a subroutine call over here. Very simply, instead of doing it the old way, where we have these as arrays. Okay? Yeah, we are not going to get to slide 70 today. So, okay, and then so now we're going to look at functions and modules, where we were going here. And why do we have subroutines? It's we have code replication, and then we can do things. We don't have to replicate code, and we can just provide different input for it. And then what we're doing in a subroutine is we hide variables in there that we're, say, only going to use. Only used within that subroutine, like I and J, maybe a scratch array or something like that. And we pass a value that comes from our main program. Okay, so that's the idea of a function call. Now what we're going to do is look at modules, and modules are the thing that's going to contain a derived type, and it will have these variables, arrays, and even more structures in there. And then it will also have subprograms as subroutines and functions and even other modules if you want to get it complicated, sort of like classes and classes. And it will have, we can talk about objects using, we can talk about object-oriented stuff, but we're going to just sort of skirt around it and give you sort of the basic things that you'll need in terms of modules, how those can contain functions and subroutines and data. Now we're at the point of your class. Your class had methods in it, and it had variables in it, and that's what we're going to do here. Now what we do here, here's another one. Here's our module. We're in module in the first place up here. We're not going to have a derived type yet. We're just going to have some parameters and some variables in here. So this thing, we start a module, and in the module down here, it's just going to have variables in it. We haven't gotten to the part of containing functions or anything. And then in my program down here, this can be in a separate compile unit, in a separate file that I compile separately. And here's my program. So this thing can be compiled separately. And in my program, I'll have program go mad. And down here, I'll have use mad science, the name of this module up here. And it will pick up everything that's here and have it available right here for this program. Okay? And that being an R value up here, note I'm not declaring R here, I'm actually using that out of this module here. And then what I can do is do print, and actually pi as a parameter was in that module too, and I'm going to use that. And so that's a baby step. A module. How to make one, put this in it, compile it, and it will make something called something.mod, and then you go down and compile this, and it says use mad science, It will look in that directory for something for a .mod file that has this in there, and it will pull all that stuff in there. So right now, it's just like a little bit of an include file. That's all you have, okay? Now, what I can do down here is now within this module here, I can also include derived types. Here I'm going to say I have a type called scientist, and here's my name, if I'm mad or not, and what's my height. For some reason, just pick those. And here's my end of my module. Okay, so we got a little bit more advanced. We just had some parameters. Now we're going to have a derived type in there. And now here's how we're going to use it. Here's how we're going to get a little bit more fancy. Here's my module, mad science. And in there, I'm going to have my parameter. I'm going to have my type I talked about. And now in my modules, I want to have a contains. And I can have functions, and I can have functions, and I can have subroutines down in my contains. And the important thing here, just like a C structure or a C class, the scope of anything here in this module is included down here for all the contains. Okay, so anything I declare up here, I can actually access down here. I'm not doing it in this case. In this case, if I call this subroutine and it's this, and I pass this, I'm just telling it to make whatever that was, which was sort of this, whatever that was in terms of the derived type. I'm going to make the mad equals true and then return it. But actually, if I wanted to make, say this was S percent height right here, I don't have a value. I can put that equal to pi. Pi is known in this subroutine from the values up here. The scope of this module, or these variables up here, extends down to the subroutines and the function in the contains. So that's like having a method in C++. And there's where I was going. And so over here, here's how you access it. So we made all that over here, and now we go to program go mad, and we use this mad science module, which is named this over here, and this was compiled separately in some other file, or you could have it at the top of this file. And then down here, I say I want a U and I want a we with 10 of these structures in an array. And here's how I make my assignments here. And I make a U, and I just put my name in U. I didn't put anything else. And then now, see, I do a call set underscore mad with the U. That's going to call this guy over here. It knows about this guy over here. And then if I want, here's my array of values up here. And for the first array, I am going to element which consists of the structure itself. So I want to put U in that first one over here. And then down here, what I'm going to do is put $true into we %mad. And this is using vector notation in Fortran. And this says all the array elements here that have a %mad, I want true to be put in there. Okay. So we'll see a little bit how that works later on. It's probably overexposure to some of the detail here for doing this and what's happening. That's a little bit more advanced. And then here I'm putting 0.5 in the structure U for the height. And here I'm accessing U %height and multiplying it by P, and P is known from the fact that I've used this. And all the things in here that I get from over here are public. This is by default all public. So when I'm in my main program over here, if I need to use a variable that's in this one, it's public, I can access it because I have the use here. Now, we can make things public and private here, and that's where you get into the C++ stuff, is making, putting restrictions on it and hiding. Here we're not really hiding anything. We're not hiding the subroutine call. We're not hiding the type declaration. We're not hiding any of the parameters here. And but that's okay. You may just want it that way. You group everything over here. You use this guy, and then you have access to the types. You have access to the parameters and to the subroutines. And what we're going to show just in a little bit here is how then to restrict access to these modules. By default, everything's public, like I said in the last one. We can declare at the beginning everything to be private, except what I might declare specifically by the colon for variables or for subroutines. So what I'm now saying is mad science, everything in here is going to be private, and then I say, oh, but I want this subroutine set_mad to be public. Here in my module, I have, usually variable declarations down here, but I don't have any. And when I have my function calls, I have it under a contains, and so I have two function calls or subroutine calls here, a reset and then a set mad. Now, private applies to everything unless I specify otherwise. So this guy is going to be private, as I say everything's private. And this guy here, because I say specifically I want him to be public, he's going to be public. And in this subroutine down here, I actually do make a declaration to a function in this module here. Function actually, it's a subroutine. And so I call reset from this guy. So outside, I'm going to call this guy. And inside here, when I do things, I'm going to call a function that's only allowed by me. So now we got your C++ stuff. Yep.
So the only part about that is public is set map.
Yeah, that's the only thing now. Now, if I didn't have this up here, if that were out, everything would be public, and I wouldn't need this statement. And if I wanted everything to be public. But we talked about when we have subroutines, the idea is to hide variables and use local variables here. Now, in more advanced methods, whether it be C++ or object-oriented stuff, you want to have these things that you use, and these things have function calls that maybe are accessible from the outside, but certain ones that aren't accessible out to the side, and that's the protection there. Okay. You can play all kinds of games with this, but once whether it be C++, Java, or anything, you get to this level where you hide things. It's like when you were a kid and you got a candy bar at the store and you weren't really supposed to eat the candy and bring it home and you sort of hide it someplace. It's just good your mom or dad don't know. It's okay to have a candy bar every once in a while. That's what you're doing. You're hiding things here because it's just best that the user not have access to it or change it. Okay? Okay, we're still with me? Okay.
I'm going to take one away from you.
Okay.
For 10 to 5 minutes.
I thought you meant, okay.
Oh. And then I'll come back for again.
Okay. And this is a little bit simpler and more to the point. And what we're doing here is that we're going to have a subroutine, something more you would do in HPC, and we're going to have a subroutine called swap. And inside this subroutine, we want everything to be private. In this module, we want everything to be private except swap, because we want somebody to call swap from the outside world. And we want, here's our arrays down here. Here's an array. We're going to work with just a standard 100-element array. That's it. And so we're going to work with this array always. It's always going to be that. But because of this private up here, this guy's only going to be private. The swap down here is going to be public, though. And what happens is you come in, and to swap an array, the easy way to do it is to have these two arrays here, one put in the temp, and then take the one you have and put it into X, and then Y gets this value that you took from X there. And that's how you do a swap. Sort of standard, normal way of doing it. But Scratch is going to be private. The user cannot access it. He never sees it. and it's just done behind under the covers there. So now this is where we wanted to get to, doing stuff like this and using those keywords of public and private. And then what am I going to do here is another example where we have these, there's a parameter and values here, and then we're going to have protected. The other one is protected. So protected means that I have the right to change it inside this module right here. I can change it, but you can see what value I'm using. If you can't touch it, it's protected. Only I can change it. So that makes sense that you want public, private, and then protected. And so here what I'm doing is actually having a value saying it's protected. And then down here in my subroutine contains, and don't forget scope, everything up here is known down here. And then down here, I'm going to, when I do my allocation, it's going to, I guess, define this value, and then make a scratch space down here. So actually, what I should do is just set this value to be 100 up here, and then down here it can see that value. I don't know why this is here, but it would be a little bit simpler if I just took this out and made n equal 100, and the user can always access that variable because it's private. Access it in the sense he can read it, but he can't change it because I'm the owner of that, and it's protected. I don't want anybody screwing around because I always assume I know best. I need 100. He can find out what that size is, but that's it. Okay. Another thing. So we had this concept of using a module, and so I can use a module and I have access to those variables and those arrays that are public, right? I can sort of see them. But what if I'm using one of those and I have a conflict? You know, a pi, for instance. I want to define pi in mine, and I'm actually using this. Some library guy wrote this and said, "Oh, just use this," and it had pi in there. Well, that's going to screw up things. You know, which pi do I use? The one I just defined locally, or the one I'm going to, or the one that I just used out of the module? And luckily, the compiler will tell you if there's a conflict. Okay, it'll tell you if you're a conflict. Well, then how do you resolve that conflict? And that's through renaming. And this is how you do it. So up here, I have pi as 3, obviously it's truncated, and I have that in my module. You know, I just have my parameters in the module up there. And then down here, I use mad science, and then down below this, I have what I think should be pi as a better number, but I may not even know that this guy did that in there, and I'm using this mad science module. And so what you can do is rename pi. And so on here, on the use module, if the compiler says, hey, he's got a value of pi that he's setting in there, and so do you. So we got a conflict. And so the compiler will tell you about that. And then you just simply go in there and say, whatever you call it dummy pi or ridiculous pi or something, and that is going to, that pi that was up here is just going to be renamed that. You don't use it or anything, you just rename it, get out of the way so that the compiler's happy. And that's the easiest way to express that. And actually up here, if you don't need all the variables in there, you can say comma only, colon, and then list the variables that you only want to access out of there. So there's different ways you can restrict what's coming in when you load, because he makes things public. I don't really have to accept all of his public stuff. He can do whatever he wants with them in that module, the developer or myself, but I want to restrict that here. And so you can do restrictions with the use command. And so when you do print mad pi down here, it'll be 3. When you print pi that you set locally here, that'll be 3.14. Okay. So all kinds of ways to do restrictions. Okay. Okay. Interfaces. This is actually one of the better things that Fortran 90 brought, and the problem also existed in C, but they resolved that by what they call prototypes. So if you want to call a function in C down here. Actually, you don't need to call, but here's a subroutine. But if you're talking C, and that's just some function, it has these lists of variables that it uses, right? And in C, you make what they call a prototype, and that says what kind of values each one of these guys are there. And so, and that's usually in a header file. You include the header file, and it has prototypes, so you can put it in your code, and boom, the compiler does it. You do the call, it knows what the subroutine arguments are, and it may say, I don't like this. You know, if there's something wrong, it'll tell you that's good. Well, Fortran didn't have that. If you messed up on your list here, there was no way to tell what was going on, and silently, if you had an integer on one side, declared it in a subroutine to be an integer, and in the call you had a real, it wasn't going to complain, and it just put trash in that number on the other side, and you'd spent a day trying to find out the problem that, oh, you made the call, and you're getting trash on the other side, and you can't figure out what's going on. So this will also happen in libraries. You make library calls to MKL or one of these places that does your matrix multiplier, your matrix inversion. You guys aren't going to reprogram matrix inversion. You guys are just going to call a subroutine. And that's going to be provided by a library. And that library out there has a particular arguments that need to be a certain way. And let's say you misread the documentation and you're putting an integer in here that's supposed to be a real. That library is going to return junk, and you're not going to know what's going on. Okay. The way around that is for the library provider to provide a module that you use that specifies that interface for you. And then the compiler knows about that interface, and it can check, and it would do like C and say, oh, hey, that's real. There's a conflict here. And believe me, that is a big time saver, because many of the mistakes in coding, the headaches that come, are passing variables through subroutine calls. It's a great thing, you know. So that's a very important part that made C, Fortran, and these languages really good, is to have functions and subroutines. But it's a blessing, but yet it is a curse. So you have to live with that. And so that's what the explicit library faces do, is to provide that. And how does it become explicit? You can declare the subroutine or the function in the module, and when you use that module, now the compiler knows that subroutine. It says, oh, you use this. Well, I know what's in there because you wrote the function in there, or the subroutine in there. And so it is, quote, officially explicit at that point. And so it will know, and it will check to make sure that A here in the subroutine, here's my module, and of course there's no in module here. And here's another subroutine. There should be in subroutine, a bunch of other things here, and an in subroutine, and say in module wherever I wanted it in there. Actually, the module is in there. So my module up here, here's a subroutine, and what I do is use this module up here, and here's my function call here, or my subroutine call. Up here, which is not shown, is right here is not shown, but should be shown, is the variable list for A. Something like real : A, B, C, integer : in. I think I'll put that in the slide. But the problem with putting more in these slides is there's only so much room. This is a LaTeX document, and I like working with PowerPoint, but it was really hard to put any more in here. But the idea here, this subroutine is defined in this module, and right under here should be how these are defined. And then I have some other subroutine or a main, and I use that module down here, and the compiler now knows what these should be, and of course the variables should have been X, Y, and Z are declared up here. So there's things missing in this example. I didn't get to that last night. I should have put those in there. But that's what you want to do, is make an environment, make the subroutine interface explicit. Is if you put these in a module, and use that module. So one reason to use that, to put them in modules. The other way to do this is you can declare an interface, and it would be the declare interface basically has in it the subroutine name and all the declarations, and that's it. And I think we have an example of that. Actually, that's going to come later. Okay, so let's just say that the modules makes the interface for subroutines explicit if you have it there. Now what we're going to do is talk a little bit about passing arrays and some things you need to know about Fortran. And that is, up here, we have a call to a subroutine where we have x as a dimension, size in, and then down here we call with x and then size in. And this is the way people did it for many years. And they would just they would have the subroutine here, and then the declaration, they would specify the argument here. So this says we have y as a dimension of size m, and now this subroutine, when it's using things, it knows that the dimension of this is going to be n because we passed it. And so that's typically what happens, and you'll see lots and lots of code like this. When you pass an array to a subroutine, it will give you the size and the array reference. And inside there, you would do this. And that works, and that's fine, and just getting started and doing that, that's good. There's a little bit different way to do it, and that's what they call assumed shape. And the way this and the interface has to be explicit for this to be used, that is, has to be known. And so what we can do is specify, here's our module, and we're putting our subroutine in the module so that when it's used someplace else, the calling routine, when it's being compiled, knows all about it. And so now what we're doing is we just pass x, okay? And we pass x in here, and we define it to say it has a dimension of, I don't know. This is very similar to the allocate. Okay, remember we allocate does this. When you allocatable, it does that. Okay, now what we're saying here is the subroutine just pass it x, and then we will use it in the subroutine right here. And in Fortran, you can say I want the size of this array, or that dimension x, and this guy will print a value here for that. You think, well, how does it know what size that's going to be? It picks it up because this is going to be an explicit interface when we use the module down here, and we call the function with just y, and we declared it to have 100 elements in here. We just ship it across to y. The interface is already known at compile time, and on the other side we put a colon, and it knows what the size of it, where it's going to be. That's something much better than what C can do for you. Of course, C doesn't have explicit arrays. And so basically, you then, if you want to have the value of m, you just use size of here. Okay? And you go, well, how good is this? How would we use this? Well, in our swap subroutine there, it's quite reasonable to use this in terms of we have that swap interface, and we say that A and B or whatever we want here, and remember we needed a temporary worked array, and we just say size A, we're going to make our worked array the size of A, and we assume these are both the same size. So it's pretty cool. Yeah? Okay. So yeah, where was I? So we do the swap right here, and everything's pretty much set for us. Now, in Fortran, what we have these lines here, you're thinking, wait a minute, don't I have do loops? I don't think I mentioned this before. Where are the do loops? Because I want to take all elements of this one-dimensional array and put it in the other one. Fortran has array syntax in it, which is part of Fortran 90. This says whatever size that array here is, and it knows what the size is. We just pass A and B there. whatever size that is. Oh, okay, here I got the size that I made work array. And so there's, say, 100 elements. It's going to say, take all 100 elements here, and element by element, I want you to move or put those in work over here. And it says, for all 100 elements here, element by element, I want to put here, as though you put a do loop in there. Okay? So that's the big thing about Fortran, is the array syntax that you can use in terms of putting, making things a lot cleaner and simpler. I mean, these are scalar. These look like scalar quantities, but they're not. They're array quantities, but we handle them like they're scalar. We don't have to put a loop by around it. And it's treated as element by element operations when you do something like this. Okay. Now, when you're passing arrays or variables to subroutine, you can specify how that's to be used in the subroutine. Whether it's just to be an in variable, or by that we mean it's just going to be read. Whether it's an out variable, whether it's just going to be written to, it's not going to be read, and it's just going to write to it as a result. Or if it's going to read it and do something to it and write to it. And so you can specify this in terms of your argument. You can specify these for these particular arguments that you have. So, and these appear as attributes. So we have our real, A, B, and C. That's fine. Our scratch is real, and the result is real. And we're going to specify their intent. And the reason you specify their intent is to help the compiler optimize things, and then the compiler will actually check on you. So if you have a variable that's only to be read, so for instance, you pass the size of an array to n for, that's for something you're using, and you say intent n, but in your code you specify a new value for n, the compiler will tell you and say, this, you got a problem with that. So it's good for you as a developer in writing code of, number one, your intent, number two, what the compiler should look for, and to anybody else modifying your routine that you don't want them changing that value. So it's good on quite a few levels to put this intent. Is it mandatory? No. It's not mandatory at all. It's just a attribute that's a good thing in terms of programming technique and programming method. Okay, and then in Fortran you can also have optional arguments. We came across one in the allocate intrinsic function. We had the status value for whether it can allocate it, and that value then you operated or checked it, but you don't have to get the status value because it's an optional argument. And it will tell you in the documentation which arguments are optional or not. Good documentation will. And here's how that is used. We have, in our module here, we have a subroutine with A, B, C, and D, and we specify A, B, and C as real, and then we specify D here as optional. It doesn't have to be the last one, the first one. It can be, usually put optional ones at the end for a particular reason. And then in the code, you can actually check to see if the user specified the value. And you can then use a default. In this case, it said, hey, is D present when this guy called this function? If D is not present, then I'm going to make, or if it is present, I'm going to make start equal to that D value, and then say increment it by 1. Else, I want to make start equal to 0. Okay? So you have, you can find out if the guy used it or not, and use your default or whatever he wants. So you can have a default for that value, and you can use that. And then when you're calling this function or the subroutine over here, you can do normal things. You can have the list here in order of what's over here, as usual. Since the last one's optional, you don't need to include it. You can specify A equals those values in that order. If you specify all of them, you can say, you can mix up the order here. And if you want, of course, you can do something like this. These values, these three have to appear there. And if they're in order here, in this sequence here, they're mapped directly to what's over here. And then after that mapping, you can have the assignments that you want in any order. So I can put D first and C here, whatever, and it's going to take these first, and you have to have, you cannot have 4 over here, something that wouldn't know what to do with it. You have the ordering first, and then any of these over here. And if you have, if these are non-optional, you have to have this, but you don't have to have it. Okay, so I could have 1, 2, C equals 3, and not have that, that's fine. But I have to adhere to the ordering for these non-optional. Ordering in the sense if I just have numbers here. If I want to declare each one of them associated with a particular variable, I can do that. Okay, but that's all, lots of times not so good because you have to go back to the subroutine wherever that is declared, and you have to find out what these are, and so that's sort of messy. Most of the time people are just interested in the order here and using that, and whether an optional one is used over here, and they might have this, actually the value used is D up here. So when we saw the allocate, we had a string of different arrays that we can allocate, and then the status equals a value we had, and that's typically what you do with something like that, because in Fortran with the intrinsics, you show there's a static and you remember that. But you don't remember what the other things are. It's usually just some sort of values here. Okay? Oh, we took a break. Okay, so we're just going to jump by these quote complaints real fast, and the idea is about C++ and name mangling. I think we'll skip that, and then how much of the old stuff should we do? None of it. And then, of course, coding can be ugly, and one of your objectives is to be able to read that code months later, and and be able to make sense of it. So adhere to that. Did any of you ever remember reading Donald Rumsfeld's quote about knowns and unknowns? And I think the thing is, like coding, you can speak a certain way and it can be very confusing, and the best thing to do is be very precise. I like the, but there are also unknown unknowns. The ones we don't know. And so it's a little bit difficult. So you can look up, I think he has quite a few quotes that, I'll just say it, maybe I shouldn't use his name, just say a politician, but the name's out. So these are perfectly valid, but as Lars was saying, the presentation is lacking. So in object-oriented coding, no, you don't have to write it. You can use the elements of it, and we see a lot of that in Fortran, where people don't use, quote, the classes, but they'll use a lot of the modules, derived types, and then functions and subroutines in the modules. That's very good. Write your code, use the modern constructs, do put comments in your code, but don't have a print statement with a variable called matrix size, and then above it saying I'm printing out the matrix size. It's obvious from the code, So don't go hog wild on documenting. Lots of things are self-explanatory. It's the complicated things that will be helpful to you later on, and somebody else looking at your code. And it could be a point of pride in terms of how well you're organized and can write code. So name mangling, we're not even going to discuss that. Yeah, you don't need to master all the things. Know about structures, allocate and deallocate, and the modules, because lots and lots of people are using modules these days. And the how do you get started? Okay, so one of the simple ways is just start putting some of your variables or arrays and even the parameters in a module and use that module. Simple, really quick way to get started. And then as things get, if things get a little bit more complicated, start using the derived types. But also, I would suggest in the modules using that as a place for your functions, so your interfaces become explicit. That's going to be very, very helpful in compiling. And then, as you're using these functions and subroutines, use the private, public, and protected things. That's going to be careful. That's going to be good, because what you'll find is that you will, once you get fairly well organized, the first pass of something like, I just need to get this done, and then it starts getting more complicated, and then you develop a better structure around it, and calling, and then having your functions and subroutines someplace else, and having lots of things done there is very reasonable. So, for instance, instead of in your main program, you have all these arrays you allocate, and it's just consuming a lot of space. You actually have in a module all those arrays and a subroutine that allocates them called myalloc. And in your program, you use that module where the user knows that all the different arrays he wants to look at them are over there, and then you say call myalloc, and it's one line that allocates all the arrays. That's pretty clean, as opposed to scrolling down through 40 lines of allocs and things like that, because some codes get that big. So that is the big thing I want you to learn about. And Fortran 77. How old that is, 77. I tell Lars, the guy who wrote this, I said I won't even mention Fortran 77. He's very, because he used some of the implicit, when he first got here, he used the implicit typing, and he ran into some problem. I told him you shouldn't do that. He said, no, this is good. He's German. Lars Kosterka. No, that's good. No, and then eventually he changed. It was funny to hear his turnaround on that. Oh, question.
Yeah, I was just kind of wondering your opinion why you function, like why do you think it's working since that function is one function?
Oh, as one as a subroutine or as a function? So one of the things is make your functions. And you can put them in a module or whatever, as long as it doesn't take a lot of time. So, and you can make, do these things, and we're supposed to get there today where we talk about programming. The most compute-intensive parts of your code are the ones you want the compiler to know about and see directly. Usually when you put them in a module, you can do that. And actually, the newer ones, you can tell you can do it in line. Basically, you want functions lots of times to be in line with where you're calling it. So on your compiler, and even now on the Fortran 2003, you can say inline function, and that will make it so that it will put it in line for you. So bottom line, you can make them as short as you want, put them someplace else, make a function out. The problem that you have is if you have a user run a function, to call that function may be more expensive than to run the function itself. And so in that case, maybe you shouldn't even put the code in it. It's real small. If it's a little bit bigger, you put it someplace else, you need more. And of course, if it's real big, you always put it. But you have that option. If you know about inlining, then of course you put your function someplace else, and it's very useful. If it's very, very small, what's that sort of function? Yeah. So we want to talk about array syntax, and we actually already did because the example came up and it seemed a little bit confusing. But we'll talk about the where, for, all, and then we'll look at the case study of update stencil, and I think we'll quit. And then we'll go to elemental functions and look at that. We won't do odds and ends. But here's the array syntax. A little bit more about that. Here's our declarations up here, single array, 1D array, 2D array up here. And what we can do is if we have A and B, we have some set values B here, we can take whatever's B and assign it there element by element. For a two-dimensional, it does the same thing over here. This is array syntax for Fortran. That's what makes Fortran really, really nice, is you don't have to put a do loop around that. If that were C, you'd have to put a do loop around that. So, or if it was C++, you might write a class to do that. Here, you just, it's one line. Very simple, very sweet. Here, what we're doing is a subsection of that. We're saying take elements 1 to 10, and that's our typical syntax when we have a colon from here to here, and we're going to put it 1 to 10 over here. Here we're going to take 4 to 5 and put it into 2 to 3 over here. So however many elements you have over here, it can go any place over here, but they have to be equal on both sides. You have to, that has to, if you subtract those two, that has to be the same as subtracting those two values. Yep.
How much you do, like, write consistent values for each array entry? Is it like the same?
It's the same like C. You can assign values, or you can have a construct declaration. We'll see that in just a little bit. Good point. We'll see that. So you could, if you had particular values, you originally put them in there, you just use a do loop to put those values in it. So you might have come through, this might be our swap routine, a special swap here. So in the main code, we might have done something like do I equals 1 through 10. Yeah, 10. A I equals real I, or you could just make this thing I here. You know, and it'll say, oh, I know what to do. So Fortran is good about taking what's on this side, converting it to a real in your end. So is that what you're? Yeah. So you know, here's how you set some values. Here we're just moving things. It's kind of what? Oh, you are? Okay, let's go through this again. So let's say this is a subroutine, and in my main program, I put integers 1 through 10 in A. So I have values, or I even maybe above that. I put values in here, do, and what does this do? It puts a 1, it puts 1 in there. Are you getting that? That I'm loading up values?
Wherever you put in this I, just applies everywhere.
No, it applies. Oh, I think that's it. So right here, my array is size 10, right? Okay. I have 10 elements. And what I'm doing right here is I have a do loop. This index is going to be incremented from 1 to 10. And when I come through, it'll go through I equals 1. It'll take A1 and put in 1. It'll make it a real. I come back around, it'll make 2, it advances to 2, it puts, or the A2, it puts 2, okay? Okay, now I had a do loop for that, right? What if I wanted to put just a single value there and I wanted to put 4? Okay, I load them all up with 4, okay? And now, let's say I want to put all my A's at 4, I want to put them into, well, let's say this is B. I want to put B into A.
Are they two different?
Yes, yes, yes. So how would I do that here? If I wanted to do that here and put, I'd have to do this normally, old style. I would have to say A sub I equals B sub I. Take one value of B, put it into, that's what I'm doing there. And before that, I had done my loop. Here's just filling it up. I equals 1 through 10, and I had B, I, and let's say I made it 4 in do. Okay, so I put 4 in here, and now I want to put all my A's, or all my B's in A. I'd have to write 2 loops, right? Initialize, and then transfer. Does that make sense? Then transfer each of the elements in that array, B over to I, after I set it up here. So let's assume that someplace I already have values in B. Okay. All my values of B, element by element, and put them over there. Yep.
Only B to A right now.
I want to follow this up here. So what I'm saying is, I can replace all this by simply saying A equals B.
Okay, so that's simple syntax.
Simple syntax, array syntax. Good. How to change things.
Change the law.
Okay. Good. And that's what's nice about Fortran. You don't have to do this step here. Now, what if I wanted to do 4 to 5? That one up there, 4 to 5, and that's going to make I 4 and 5 in here, right? And then I want that to go to 2 and 3, so I have to do a I minus 2. Okay? That will work. That will do what this does up here. I 4 and 5, and then if I subtract 2 from I, that'll give me 2. If I subtract 2 from I over here, that'll give me 3. That's what's over there, and so that's why I do this here. I minus 2. But I don't have to do the do loops. I just simply state the sequence of those numbers, and as long as I have 2 values on this side, the compiler goes, okay, 4 and 5, okay, I need to put that in location 2 and 3 over here, element by element, like if it were a do loop. Okay, good. Okay. So that's good. Okay, and what's really, really nice about this is I can do this for strided things. This can be strided. So this says take elements 1 through 5 and just go at stride 2, which means takes elements 1, 3, and 5. That's the stride. 1, 3, and 5. 1, 3, and 5. And push those over into 1, 2, and 3 over here. And you think of it as doing element by element. So you can say take the 1 over here, put it over here. Take, oh, we got a stride by 2, take 3 and put it into 2. And we got a stride by 2 here, and so the next value is going to be 5. Put it over here. And it's just like we did the game we did down here. Over here, for that one, we do a more complicated game. And so lots of times that's what's being done in calculations is you're striding over things. And it occurs so often that in Fortran 90, they said, well, yeah, we'll make this a triplet and say the other value here is a stride. These are sequential values in here, but oh, wait a minute, let's make it strided. And so that's how you can do that. And it will take these guys and put them over here. So you don't have to, you know, it saves you from writing those, quote, nasty do loops all the time. Okay? Okay. And then you were talking about how do you fill these up. Of course, we can do something like this, perfectly legal, but now we have more ammunition. How else can we do this one? Well, you have to know one little thing. So if we can do this set 4's views, but all these B values over here, but we can also do this. And the compiler knows this is a scalar value. This is a vector or array, or whatever you want to call it, over here. And it says, oh, well, I know what to do in this case. Element by element, this is a scalar. I want every single one of those to be 4. That's a good way of just loading up zeros. Lots of times you want to load up zeros instead of doing this. You do this. So, really easy. Array syntax is your friend. Okay. On how to do this, array constructors. If there's, we have lots of little ones, you just want to load up a few values, 10, and you can do that by hand, and you can do that with this type of specification. Here we're saying our dimension is 4, here's x, and here are going to be the element values. So lots of different languages sort of do it this way, whether it be squiggles with the list here, and I'm missing a comma there. There's a comma missing right there, okay? And here I'm going to have x and y, and here is where I do it in the declaration. So they're going to be saved that way right when the code starts. Here I'm doing it as specifying it as a statement in the code. Yep.
How does moving throughout arrays change if you have more than one dimension?
Let's get there later. That can take a little bit of time. But you have a nested do. You typically have A, I, and J here, just like on C, except we have parentheses. And you have a do I and a do J. And you can actually, what's really nice is you can just take sections of those. If you want to take just a column or a row, and with array syntax, it's much, much easier than trying to do the do loops and figure out if you have the indices right. So, and I think we have an example of that. So, and here's what we do with allocatable. We have an allocatable array here. Now you feel a little bit more comfortable. And X, and what you can do here is now that this is an allocatable array, and this is special in the newer Fortran. You don't even have to allocate it. You can just make an assignment like this, and it will make the size of this 3. Or if you just make it and then later on use it as 4, it will just use part of that and declare that as the new size. You don't see a lot of this. This is brand new. It's a little bit hard to think that, oh, I have this allocatable and I didn't do an allocate on it. But that's what you can do. It actually takes all these values, deallocates what's over here if there's anything, and then allocates it and puts it here. And so that's what happens each time. So down here it says, oh, I already did something with X, deallocate it, and now allocate it and move my space over there. So that can be expensive. So you don't want to do that in time-consuming code to do this kind of thing. You just want to allocate once and reuse it. So, but if you do things like that, yeah, that's shorthand, that's nice, but it's a little bit expensive. If you're talking about arrays of, hundreds of millions or something like that, then you're talking, but if it's short, no problem. So here, oh, and you can have derived type constructs. So this is derived type, and if we want to put something in U here for these 3 different values, you can just make that a list here. So that's pretty handy. Yes?
So the last slide was are those 2 the same thing?
Up here,
What's the top of
they're doing the same types of things, just different syntax. Continue here. This is an allocatable one, and I'm stating down here that gets allocated on the fly. These guys. I have a constructor of array elements over on the right, and if I have an allocatable, that will allocate that on the fly and put these values in there. So if you have an allocatable up there, that's sort of new. I think for beginners, don't worry about it. You're not going to see that. You're going to see stuff like this, and then in Fortran, you'll see this used throughout. So for instance, I know this should be a bunch of square roots on some real numbers, and it's very convenient to have this syntax. So something in parentheses here with a this sort of like a do I equals 1 through 4, and this sort of these outer parentheses are sort of like that do with something to be evaluated. So that's very, very convenient. But basically, more advanced people start using that. You don't need to do that. And then what I want to say here is derived type constructors. You can have a comma-separated list that goes element by element into the derived type, just like an array. Array, we have these values. We put in if I an index, I equals 1, 2, 3, and 4. we're putting those values in there here, and with a derived type, it's the same way, except it's element by element. It's sort of like, you can almost think about, well, it's not a hash, but it's getting close to it. Okay. And then the indices, of course, in Fortran, you do this in C too, is you can have, you can use an index of an index for something. So if we have an array of values in here, 1 through 9, and now we have an array of two values here, we can use array syntax notation, and this says basically that the array of 2 and 4, it's going to print those two values out for A here. So you can use an index array inside an array. Okay, that's helpful sometimes, but it's beginning. Lots of beginners don't necessarily use that. And then this is reasonably good to use, the where statement, and it applies to arrays. And this says where x, I have an x array up here, and it says where x is less than 0. Let's see, is this an integer? That's okay, 0.0 that should be. What I'm going to do is make an assignment that that's going to equal to -1. And so you start the where in the where, and you then, wherever the values are applied to this array, wherever they're less than 0, you're going to make those corresponding values in A be equal to -1. Okay, so this is array syntax, and that's what makes it really powerful, is how simply you can write things, and it's once you've seen it a few times, it's relatively easy to understand. And here's another example where this says if x is not equal to 0.0, that should be, then do this, and then elsewhere to make the A is going to be 0. And I think I have this example called where.f90. You should run it, play with it, just make sure you comprehend it. So that's very powerful, the where, the for all. And let's see, this is another one. It's just want to point out that functions, when you call functions, they, we're talking about vectors now, those functions can be scalar, meaning it's going to do something just to that variable. So here b, right? And it's just going to put a random number there for you, and b is a scalar. And up here we have 100 by 100, or it could be 100. It doesn't have to be multidimensional. It would be more reasonable if ever we use just a single 1D array. Here we have an array, and down here, what's neat is you call in the same function with an array, and it's going to do that operation on an element by element. So here we get one random variable, and here we're going to get multiple 100 times 100, 10,000 random numbers from this intrinsic function. So in Fortran, that's pretty neat. You can hand it a single variable, or you can hand it an array of values, and it will do that operation for you. Pretty cool. So if I wanted to do a square root on an array of values, I just stick the array in there. If I wanted to ask some questions about that, I can do the operation on the arrays. And that's what makes Fortran very powerful. And then there's the any statement that says if any of these is, say, greater than this value, or you might have 0, you're testing if it's going to be equal to 0. If any of these exist, then you're going to say print this. And where might this happen? You're looking for the bad number in a big array, or one of your two-dimensional array. You know someplace in there a 0 is causing some problems, or a negative number is causing some problems. How do you find it quickly? And this is an easy way to do it. You say, hey, any of these guys 0 or -1 or something like that, go ahead and pick it up and use array syntax. So it's very, very powerful in that regard. And then here is some stencil code, and I do have the stencil code out there. It's something to play with. But I want to show you in terms of, this might take a little bit to explain. And so I should have a gulp of coffee first.
Why haven't you included this here? Like,
This one,
Yeah.
because we have to do something special. Okay, good point, good point. So one of the things here is you always have to watch out in going from your formula that you see, say a stencil operation, for this in terms of what's going to be happening. And you want to do this as a formulation that you see. And what you will see in different codes is they don't want to waste space by putting not having extra space. They want to write into the same values that they've been using. So if you look at that formula there, and it's supposed to be doing this. So we'll take a sub 2, and that is going to be equal to a sub 1 plus a sub 3 divided by 2. And then what we want to do is put that, we want to hold that off, and let's put that to T1, because the next thing we want to do is do a sub 3, and that is equal to a sub 2 plus a sub 4 divided by 2, and then a sub 4 equals a sub 3 plus a sub 5 divided by 2. We want to have, when we're finished, and I'm going to call this A sub 1, 2, 3, 4, 5, 6, 7. What we want to do is get these two values, eventually put it in here, but we want to get these two values, and eventually put it in here, and get these values, and two values. Let's see, 3 and 2. I want to get these two values. Yeah, I need one to go in here. And so what I want to do is save this value. I don't want to put A2 in here immediately because I want to take averages. And the best way to actually do this is to say B sub 2 equals A sub 1 plus A sub 3 divided by 2. B sub 2 equals A sub 2 plus A sub 4 divided by 2. I want to take an average, an average, an average, an average, and I want to put it back in the value. And the way I should do this is take the average of 1 and 2, put it in A sub 2, because then I'm using it down here. I want the original one, and then put that in B3. Put A sub 3 plus A sub 5 divided by 2. And then at the end, I want to put B2 to some end value here back into A 2 some end value. That's array syntax, but this is what I wanted to do in terms of the operation. So I had to be careful about doing this correctly, and if I do it in a loop, like I do here, and it's a little bit complicated, what I'm going to do is I'm going to hold off putting this value in A2 until I've done this. And you don't have to know the details, but basically that's what I'm doing here when I make this temporary value. I'm going to hold this value off in here, and then later on I want to make it into, right after I do my operation, then I'm going to get T2 back for the next iteration. And that's what's happening here. So it takes about, it takes a little bit to go through that, but basically I'm avoiding doing, I can't do vector notation or array syntax on this because I want to hold off that value. So I have this loop. I might have written it this way to begin with. And the big question is how can I do that with array syntax? So this is pretty complicated. You know what I want to do, but I can't make this assignment here and then use it here. I need to be careful
everything on the site first, right? By putting it into a temporary and then pulling a temporary back. And that's one of the key things about the way array syntax works, is that everything on the right is done first. And so now we go into how would you do this if you were writing in an array syntax. And here's the thing, when I was talking about concepts, is that this is what you might write down, but this is not what you want to do. This formula, the way it's written up there, is sort of wrong in a sense that we don't want to. We want to do that element by element, but hold off on A. And you'll find lots of computer scientists and people even talk about doing these things, but they mean that I want you to do this kind of thing, put it in an array here, and then put those values in, because I want to use an average of those values. The wrong way to do it would be to actually, the wrong way to do it would be to go through a loop and do it that you were first suggesting this way, because I'm clogging, but you didn't know enough about the formula. And that's the thing, you go from a formula, you go over here and go, oh man, I can't do this. Okay, and I want to use the same space, but this is going to do those kind of things for you. So different way of thinking about the do loop and the array syntax. The array syntax for all those simple things is very simple and easy to use, good to get started. But the way to think about what's happening in array syntax is all this is done first, and then it goes over here. And if you keep that other aspect in mind, that is the one key part about going to advanced Fortran, is that's what's happening. And if you got, it looks like you, from your, I look at you, it seems like you caught that. You caught the drift on that. And so that is really good. And it does, in essence, what I was doing over here. It says, I'm going to evaluate all these and make sure that they're temporary, and then I'm going to push them over when I'm finished. So there you go. And I think, so in the stencil update, this is a two-dimensional now. Somebody said, yes?
I was wondering why you started with your first value. In the previous slide, the first array value used was the position 1.
Yeah, because we need that for this right away. Right. If you go through the logic, you'll see.
Right, but I'm confused why you wouldn't start with position 0.
Actually, you can't. You have to go from the first one has to be 1. Actually, you know, it depends where your starting point is. Right. Our starting point is going to be, and you notice I started off with 2. Oh, that should be 3, and that should be 4. Yeah. Okay, that's 2. That's 3. That's 4. So my first value has to be 2 here. My first value has to be 1 and 2, because I'm taking this average and this and this. And if you go to the logic, I'll sit down with you. You have to first have the 2 value that you set up here, and that has to point to V1, because we're starting off with V2 over here. See my index, and that might have, see we start off with I2.
So you could shift everything. Yeah,
you can shift, if you're in C, you could shift everything. But what's really nice is this is, and we had to go through a lot, and just right there, you're going, oh, if you think in these kinds of terms down here, it's a lot simpler. Everything on the right, and then now somebody wanted to know what you do with multi-dimensional, and here's a 2D array right here, and we have nested loops. So we have our do outer, our do inner, and note we have different indices here. And here's how we do it in Fortran. Looking at those, instead of 1D, it's 2D. They're separated by a comma. So this is the row, and this is the column over here. And you always want to have, in Fortran, you always want to access down the row first. Just remember that. Fortran, the first one you want to move the fastest in the index for accessing from memory. So remember, Fortran is first. C, it's actually the opposite. Okay? C, yeah, exactly. You had it. It's like, ooh. And so there's problems in going from C to Fortran in terms of accessing, because you want access from things from memory sequentially, how it's lined up. And when you assign these values here, they're always lined up 1, 1, 2, 1, 3, 1, 4, 1. They're always lined up in memory that way. And so you always want to pull them out of memory that way. Otherwise, you're picking out, if these two were reversed, you'd be picking up the 100th, the 200th, the 300th, and that's not good, okay, for optimization. So here they are here. We're doing sort of the things we did before. Here's what we're doing. And now what do we do? You know, before, we were putting these values back into the same array, and that created a problem. And so how can we do that with this array syntax? Here it's a little bit different. We're doing it, you know, the way you see it done lots of times, in that whatever these values are here, we're assigning, making more space. So here, making life easier and not having to do something more complicated, we say, oh, just give me some more space. Here's A over here, right side, there's no problem. And then down here, though, when we come back through the loop, what we want to do, if we want to get back into A, we have to do our assignment. Sort of like what we were doing over there in 1D. Okay, so we're doing that. And then you can do it this way. The stencil update. Yeah, it's not too bad. The indexing is a little bit of a hassle because you have to know the end values to go to and start. So you start 1. So let's go back here. So you know that I minus 1 plus 1, so minus 1 plus 1, and those are the J's. Let's go here. And if we start at 2, we know that it's minus 1, which is going to start at 1. And I think that's right. And then 2 here, and you have to know the ends. I have to look at this again. But basically, you have to know the start and the end, and it's element by element. And you have to do this. These are basically offsets in here. So if we have 2, 2, taking for all these over here, then our 2 to n minus 2, 2 to n minus 2, then we're picking up the 1 to n minus 2, the 2 to n minus 1. Yeah, that's a little bit, yeah, it's a little bit more of a hassle. But we have, you know, that was a little bit of a hassle, but we have the for all for this. And the for all looks more like your program before, like what we did for the do. But actually, it's everything on the left, do it over to the right. So here's our A's over here, but do everything over here. Now, it's pretty much like the last one. You know, when you wrote this do loop here, that's complicated. And then you take that same values there, and now what you do is put a for all on. You put the for all there, and that's one statement, and so we put an ampersand to continue. That expression there is identical to this one up here. You had to say where you start and where you end, where you start and where you end there, and likewise, where you start and where you end, where you start and where you end. Same thing. One-liner.
Syntax is just really crazy. Like, I feel like if I took like a Fortran class, this would be so great. But oh my god, this is so crazy.
Yeah, you will get used to it. It depends. So what I've tried to do was that you have to decide. You know, we're mind dumping on you here. You know, with all kinds of things, and that's okay. You know, feel over living, you do. And I'm still learning things, and I've known this for 20, 30 years. But the important thing are these high-level points that we can get across now, so you can feel a little bit comfortable. You know, you think, do I want to take a Fortran or do I want to take a C? Or how much do I want to get into this? And sometimes, you know, you say, well, there's a certain high level, and the best thing to do is go to the high level. What are the high-level concepts I can use and put into a program? And I picked these high-level concepts from something somebody else did. It's crazy to rewrite stuff yourself, okay? You don't want to do that. You want to use libraries, and so what you want to do is have the libraries do the work for you, but you have an efficient way of capturing, sort of setting up the libraries. And you can do that with this. It takes a little bit of work, but you don't have to learn how to write all the details here. And you can go back and look it up. But at least you have the concepts we want to get across is that Fortran has allocatable memory, that it has derived types, that it has array syntax that you can use, and it's quite easy. And so if you go look at some of these, you know, and go get some examples and look at them, you can start at that level instead of starting at the bottom and saying, oh, I just know these basic elements, and I just got to go and do this. Well, you can get to some of the top level stuff without too much pain. But you have to be exposed to it first. And the first time, when you're a kid and you're learning to speak, there's no cookbook or anything. You just sort of learn. You know, the first time you hear it, you have no idea. You go, da, 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 da. And later on, words start coming out. And that's the way it is with a Fortran language or a C language. And you have options here. And these options, you have to have that first exposure. And that's what I wanted to get across today. It's these sort of major concepts. And yeah, we're not going to do all that. Yeah, that's even a little bit. Yeah, so we're going to stop here. And maybe this afternoon, if you want, if you have time, you can uninstall that file and just look at these and compile it and run it and then change something. And then now, we'll find a good book. There's some references at the end. You read a little bit and get started and move along. But you're 100% right. It's a lot to look at. I meant it to be this way in the sense that I don't think I could have gotten to this level if I had started covering syntax and didn't start racing headlines and things and saying, oh, understand this or you'll get this later on. So, and this is the first time I've taught this. But I've known Fortran for years. Yes.
So far, I would completely like
but you have to tell it. Yeah, and it'll do that. But usually people don't go 7 dimensions.
Well, yeah.
Yeah, 3, maybe 4.
Just as an example.
But 3 is about crazy. You got it. So, what are you guys doing this afternoon? Huh?
Is there an
there might be, it depends. I am not kind of, but I would write a 4 all to begin with.
Yeah.
And then, yeah, you could, and it doesn't take yeah. It's not, you know, once you get used to writing it.
Yeah.
Okay, so we're officially done, let's say 9 minutes ago. Is there lunch tonight?
I think there's lunch, Valerie.
Can I end up, Valerie, can I have a lunch? So if you want to try the examples of compiling and running them and asking questions while you're eating lunch, I'll